Hello and welcome back to chemistry. Today we're going to be discussing the quantum mechanical model of the atom and electron configuration. So in a previous video we talked about the structure of the atom. We said that there's a nucleus that has most of the atom's mass, we've got protons, we've got neutrons, so it's positively charged. And it's relatively small in volume compared to this big ginormous electron cloud we have around the outside that has not a lot of mass because electrons' mass is basically negligible compared to protons and neutrons, but they do have charge, and because electrons are on the outside, we really care about them because they're going to be the ones that are making bonds by interacting with other nuclei of other atoms. So we want to know where they are and how they act. But the thing is, as we discussed before with Heisenberg's uncertainty principle and Schrodinger's whole unpredictability thing and his equation that's too complicated for us in general chemistry, it's hard to predict where an electron's going to be. Electrons are kind of unpredictable. But there are some things we can predict about them, and that's what this video is going to be about, is how can we take something that is really uncertain and predict everything we can about it so we can predict how atoms will act and how they will bond. So we're going to be talking about something called the quantum mechanical model of the atom. And that sounds really complicated, but we're going to break it down. And the first thing I want to do is go back in our timeline. If you remember from before, if you watched my Meet the Atom video, we had a big timeline with all the history that led up to discovering how the atom looked. And before all this uncertainty stuff, we had a guy called Bohr. And Bohr did something called atomic spectroscopy. And basically what that is when an electron is in a certain energy level, a certain distance from the nucleus, it can get excited by going to a higher energy level. And when that electron gets excited, if it goes back down to what we call the ground state, that's lower energy, conservation of energy, we can't just poof energy in and out of existence, so we need somewhere to take that energy. Where is that energy going to go? It's going to be released in the form of electromagnetic radiation, aka light or UV rays or microwaves, depending on how high energy this transition is. So what the heck is the quantum mechanical atom, or the quantum mechanical model of the atom? It's saying that when Bohr took these emission spectra, when electrons got excited in a certain atom and then they fell back down and light was emitted, Bohr kind of expected to see a rainbow, because can't electrons just move around anywhere they like? And then if they get excited and fall down, which doesn't take a lot of time, if they do that enough times, wouldn't they just cover every energy of light and then consequently every wavelength, because wavelengths of light have different energy? Wouldn't we expect to see a rainbow? But we did not. Bohr did not see a rainbow. He saw lines. So that told him that electrons can't just go wherever they like. They can exist in certain energy levels, and when they go up in an energy level and get excited, or when they fall down, they can't just go whatever distance from the nucleus they like. They have to be in a certain place because they have to release certain energies and certain wavelengths of light. And the way that this works, we call this discrete because it's like 1, 2, 3, or like certain numbers of wavelengths of light, not like 1.575256 or whatever irrational thing. What I mean to say is that electrons can't just go wherever they like. They can go in a finite number of places, and they can't go anywhere. And that's why we call this the quantum mechanical model of the atom, because quantum literally means counting. It's the fact that we can count the energy levels where an electron can be in the atom. So when you hear about quantum and you think, wow, that sounds like some crazy sci-fi stuff I'll never be able to understand, they're just saying counting, but they're saying it in another word. So back when Bohr was doing these experiments, he looked at the atom as if it was a mini solar system, right? So like the nucleus would be like the sun, and the electrons would be like the planets, and he thought the electrons orbit around the atom. Now we know that electrons move a little bit more randomly than orbiting, but we still, because of this, designate the places where electrons are probably going to be. We call them orbitals. So one orbital is one place in the atom where a pair of electrons is likely to be. And electrons do travel in pairs most of the time. So an orbital is actually, it's like a probability density map. And that also sounds really complicated, but it just means that like it's a map of the atom that shows how likely are you as an electron in this orbital to be in whatever place. So for example, here in this orbital, the electron is more likely to be here where things are more dense than here where things are not. And that's all an orbital is. And as you go through different energy levels, you get different shapes of orbitals, aka there are different places in the atom where the electron is likely to be. And when we describe these orbitals, we like to use a set of numbers and we call them quantum numbers. So there are 4 different quantum numbers, and basically every orbital has a unique set of these 4. You can't have 2 orbitals that have the exact same quantum number for each of these 4 categories. So the first quantum number is called the principal quantum number, and this just says what energy level are you on. Are you on level 1, level 2, level 3, all the way up until level 7? And each of these quantum numbers, or the first 2 at least, are connected a bit to the periodic table. So we've organized the periodic table so that we can kind of see the quantum numbers. And when you look at the periodic table, when you look at the different rows or periods, 1, 2, 3, 4, 5, 6, 7, that's the principal quantum number. So if I'm looking at hydrogen here, it's 1 electron because it has 1 proton. Its 1 electron would be in a principal quantum number of 1 because it's in the first row. When you get to atoms that have more electrons, you have some electrons in level 1 and then some in level 2 and some in level 3, and they build out from the inside, and we'll talk about that more later. The next quantum number is called angular momentum, and you don't have to worry about what angular momentum is, but essentially this quantum number is for the subshell. So inside each shell, 1, 2, 3, 4, 5, 6, 7, there are subshells, and we have numbers for these subshells, 0, 1, 2, etc., but nobody ever really uses those numbers. We more often use the letters for the subshells, and the letters are kind of random. They are S, P, D, and F. And this periodic table shows you where these subshells are when we're looking at the table. And I know this might sound confusing because, wait, I thought these subshells were in the atom, not in a table. But every time that you go up in protons, so you go up in protons through here and through here and through there, you go up also in electrons. So each element, if you're looking at atomic number, has 1 more electron than the last one. So the electron in hydrogen is in the S subshell. The electron in helium is in the S subshell as well, and they're in the 1s subshell because they are in the 1 shell, or the 1 energy level. And if you go to lithium and beryllium, which are the elements here, they have the 2s subshell for those 2 extra electrons. So now we have 2 electrons, for example, in beryllium, which is here. We would have 2 electrons in the 1s subshell and 2 electrons in the 2s subshell. And then if we're looking at like boron, which is here, we would now also, on top of all of that, have an electron in the 2p subshell. And we build on that and build on that. And that principle that says that we're going to build from the low energy to the high energy, it's called the Aufbau principle. And I should not capitalize that because Aufbau was not a guy. A lot of these principles we learn are named after old dead guys that discovered things in chemistry. Aufbau was not a person. Aufbau is a German word. Auf is up, bauen is to build, so Aufbau is building up. We are going to build up from the bottom, 1s, all the way to the crazy stuff like 7f. And then we have magnetic quantum number and spin quantum number. So magnetic quantum number just tells us which orbital we are in within the subshell. So in the biggest level of organization, we have shells or energy levels. Then we have subshells. Now inside the subshells, we have orbitals. And it's kind of like in biology. Some of you maybe took biology before chemistry, and you know how there's like cells in a tissue, in an organ, in an organism. It's like that, but it's for chemistry. So in the subshell there are lots of orbitals, and an orbital, like we said, contains an electron pair. So actually there are some subshells that only have one orbital, and those would be the s subshells. So 1s, 2s, 3s, all the s, because there are two columns here, there are two groups of elements, we would only have 2 electrons per shell, because every time we get a new element, we add more electrons. But in P, there are actually 6 elements across in this P block of the table, and etc. all the way down. So there would be 6 divided by 2 is 3 orbitals, because you have 6 electrons in every P subshell, you need 3 orbitals to contain them. And then we have something called spin, and spin just says when we pair up electrons, one electron has to have an opposite spin from the other electron. So one electron will have a spin that we call positive 1/2, and the other electron that's paired with it will have another spin called negative 1/2. And the fact that they can't have the same spin if they're paired together is called the Pauli exclusion principle. And these names are kind of important because they might come up in like test questions and stuff for you. So knowing all of this, oh, and I should have mentioned that for the s, p, d, and f orbitals, these little shapes I've drawn, this and those, these are those probability density maps I was talking about, like where the electrons are likely to be. So for s, it's a sphere. For p, they're shaped kind of like a dumbbell. For d, it looks like a flower. And for f, I should tell you now that you rarely ever see f in chemistry. You'll do like 2 electron configurations for f, and you'll never see it again, ever. So you don't have to worry about what the f orbital shapes look like. If you are curious, they have like more lobes than d. So maybe they have like that for one of them. They really do look like flowers. But I would not worry too much about the f subshell at all. So, FF. Knowing that, we can look at electron configurations, which is like how are the electrons organized in a given atom. So we can start at the very beginning and look at hydrogen. So for hydrogen, there's only one orbital that we're looking at, and that is going to be the 1s orbital. The 1s orbital is the only orbital in the s subshell, and in the first row of the table, we only have 1s. We only have one orbital in our whole entire energy level. So we'll have 1s, and we like to symbolize the orbitals as little boxes and the electrons as little arrows. So by convention, we always put the first electron in the box with the spin going up, and that's an up arrow. If I were to make this into now helium, I would add a second electron that was going down. So now the 1s subshell and the 1 energy level are filled. If we go on and we look at lithium, now we have 1s, and then we also have 2s. And which way is this electron going to be spinning? It's going to be spinning up. Why up? Because we felt like it. It could have been spinning down, but our convention is just to put them spinning up first. And then if we add on another electron for beryllium, because each time I'm going up in these elements, I'm going up by atomic number, so we're adding a proton, so we also have to add an electron. So if I'm writing the configuration for beryllium, and the order of writing it might not seem important now, but it gets kind of important, then I would go, okay, I have 4 electrons. How do I fill them up? From the bottom, I'm going to fill this shell, the 1 shell, and then I'm going to fill the 2 shell. And those each so far have only 1 subshell and only 1 orbital. But it'll get more complicated because when we get to boron, we're going to be looking at the 2p. And the 2p subshell contains 3 orbitals because it can fit 6 electrons, and 6 divided by 2 is 3. So for boron, I'm going to add 1 electron spinning up in one of these boxes. And now things get interesting, because if I put down the configuration for carbon, then where am I going to put the second electron in the 2p subshell? Do I put it here? Do I put it there? Well, the answer is not where I just put it, but actually more like the first one. I would put it here. So the reason for that is something called Hund's rule. And Hund's rule was introduced to me, at least, as the bus seat rule. So think about a time that you've been on a train or a bus or a subway. Some seats are taken and some are empty. So you have like rows of like 2 or 3 seats and some people have sat down and there are some that are empty. If you're all by yourself without a friend, are you going to sit with a stranger or are you going to sit in an empty seat? You're probably going to sit in an empty seat. Now picture that it's rush hour and everybody's going to work or school and all of the seats have one person in them and some of them have 2 people in them. You have to now sit with somebody. Even if they're a stranger, you don't have a choice. So, for example, with carbon, these electrons would be unpaired. And then with nitrogen, same thing. And then with oxygen, we add on a new electron and it has no choice but to sit with somebody else. And it's going to have to spin down because of the Pauli exclusion principle that says we cannot have 2 upspins in the same orbital. So an important addendum to this is that we still have to follow the Aufbau principle when we follow Hund's rule. So for example, if I'm looking again at oxygen, the way that I would fill this would not be like this. Although it comes out basically to the same thing. But like for earlier ones, like for boron, for carbon, like you don't fill the 1s, 2s, and 2p up with 1 and then go back and fill everybody with 2. You go by who has more energy. So the 1s has the lowest energy, so we're going to fill that first. And remember, we're talking about oxygen. The 2s is the next up in energy, so we're going to fill that. How many electrons do we have? Oxygen has an atomic number of 8, so we have 8 electrons. Because we have 8 protons and we're neutral. So we've used 4, 5, 6, 7, 8. And that's how you know how many electrons you have, is to look at the atomic number. And the reason that I now apply Hund's rule to these guys, but not at the same time with all of those guys, is that orbitals that are in the same subshell, like the 3 orbitals in the 2p, they are what we call degenerate. And in chemistry language, degenerate means they have the same energy. So if we go back up and look at this diagram, which I meant to show you when I was explaining the Aufbau principle, this is showing how different orbitals are in the energy continuum. So like who has the least energy, who has the most energy. So we can see that like 1s is way down here, and then we have 2s, and then all the 2p's are the same. Same energy, degenerate. That's what we call it. I know it's like kind of weird. And then we keep on going up in energy. So you just fill up based on energy. And then when you have multiple orbitals in a subshell, so like 3 in the P subshell, or in the D, we're going to have 5, and the F, we're going to have 7, you can fill them all in 1 and then 2 electrons with Hund's rule. And we don't always have to write out these boxes. They're helpful for explaining the Hund's rule and the Pauli exclusion principle, but later on we're going to ditch the boxes, and we write this in a little bit more of a short way. So for oxygen, we would say we have 1s, and there are 2 electrons, so I'm going to put a little exponent of 2, and we say 1s2. And then we have 2s, it's got 2 electrons, 2. And then we have 2p, and there's 4 electrons in the p subshell, so 2p4. So you can see here we don't have to worry about spin, we don't have to worry about Hund's rule. And we can check our work because 2 plus 2 plus 4 is 8, and that's the atomic number of oxygen. So we know that we've done things correctly because we had the right number of electrons. And just as a review, the principal quantum numbers in this electron configuration would be 1, 2, and 2, right? So if I'm looking just at 1s2, the principal quantum number is 1. The angular momentum quantum number, see, it even feels weird to say that because after this, you're not going to say that anymore. You're just going to say the subshell, is 0. Why the heck is it 0? because in angular momentum quantum numbers we count 0, 1, 2, 3, and the letters go with it, S, P, D, F, and it's literally just an order of appearance. So if we look at the periodic table, and I'm going to look at like the real bona fide periodic table here that has the F block where it's supposed to be. When we go through, we first see S, and then we're going to see P, and then eventually farther down we're going to see D, and then even farther down we see F as we get to these last two rows. So S is 0, P is 1, D is 2, and F is 3, but again, you're not going to use those when you do electron configuration. Like, nobody's going to make you say 0 instead of S. And then, yeah, this is the electron configuration, and it might seem a little bit simple now, but that just means we're ready to add on more. So, how do we do things when we get down to the transition metals, aka the D block? Well, let's pick an element, and let's practice. Let's pick titanium. So, we start in the first row. We're going to go through the first row. So 1s, and we have 2 electrons in there. And the atomic number for titanium is, I think, 22. I'm doing this from memory. So we're going to try to add up our electrons to 22. So 1s2, we go through here. That's 2s2. We're going to continue here. That's 2p, and we have everybody in the 2p, so we have 2p6. We have 3s2, brand new territory. We were never in 3s before. 3p, and that's full, so it's 6. And I know I'm doing this quickly. If you forget how many are in the s or how many are in the p, if it's full, you just count. There are 2 columns in the s block, and there are 6 columns in the p block. And then we get down here, and this is going to be 4s2, and then something weird happens. So all of the D's are set back 1. So even though these are in the 4th row of the periodic table, they are actually in the 3D subshell. So the electrons, the last 2 electrons in titanium, are in 3D 2, because there are 2 of them, represented in the periodic table when we go through scandium titanium. Right? So if we count these up, 2, 4, 10, 12, 18, 20, 22. Okay, we did it. We have 22 electrons. And I know it's kind of weird for us to say 1, 2, 2, 3, 3, 4 backwards to 3, but we are following the Aufbau principle, because if we look back at our energy diagram, the 3Ds are higher energy than the 4s, so we fill them in afterwards. If you don't want to write out this whole thing, if your teacher allows it, you can do something called shorthand. And shorthand means that we're only going to use in our electron configuration the outermost or valence electrons. So the last shell of electrons we call valence. And that, in this case, would be these guys. Usually, we only count the s and p as valence electrons because the d's are set back 1. But in transition metals, aka the ones that actually end on a D, the green guys here, we count the valence electrons from the D as well. So we can take all of this, which we call, so these are valence, we call these the core electrons, and we can look at this configuration and say, hey, this is the exact same configuration as if we were to do the configuration of argon, and then not continue into 4s and 3d. If we just stopped at 3p6, that would have been the configuration of argon. So what we can do to write this in shorthand is we put the noble gas, the previous noble gas, and remember the noble gases are these guys, that last column, in brackets, and then we're going to put the rest of it here. And that's really helpful once you get down to like these guys or those guys. So, speaking of, we can actually try one of them. So, I'm going to pick a new color so I don't have to erase all of my arrows. We're going to do pink. Let's say we want to do the configuration of, let's say, lead. we're going to do lead, which means we're introducing F block, right? Because remember up here, lead would be like there. So we are going to get into the F block. So doing shorthand, we would have the previous noble gas, and that is xenon. So we can put xenon in brackets. And then we're going to start on this row. So 7. So I'm going to label these actually. Or 6, sorry, 6. And these are 6 and 7. Remember that the F block is kind of like Alaska and Hawaii on a US map, where they put it in a little box, but it actually goes somewhere different in the real geography of this periodic table. So when we're going across the row, we are actually going to go S and then F and then D and then P. So we have xenon, and then we're going to start here with cesium, barium. So that is 6s2 because we have both of those electrons. And by the way, here the atomic number thing does not work. You have to subtract the atomic number of xenon if you're going to do that work checking hack. And then we're going to go through 6f because that is next. And in the F subshell, we have 7 orbitals, we have 14 electrons, and we can count 14 columns here, and that's how we know. So in F, we set it back 2. So S is normal, P is normal, D we set back 1, so the 4th row of D would be 3D. F we set back 2. So the 6th row of F is 4F. How can we make sense of this or remember this? Well, remember that the first thing that we see for S is 1s. The first thing that we see for P is 2p, because P isn't in the first row. So when P starts, it is 2p. When we first see D, we see 3D, even though it's in the 4th row. And when we first see F, we see 4f, even though it's in the 6th row. So we're just counting up 1, 2, 3, 4, SPDF, when they appear. So we have 4f, 14, and then we're going to have our D block next. So I have to move this in order for it to fit. We're going to have 5D, 10, and how do I know that it's 5D? Well, these are 3D, these are 4D, so the ones that I'm on right now are going to be 5D. Or you can look at the row, say it's row 6, Ds are set back 1. And there's 10 columns, so we have 10 electrons, aka 5 orbitals, but that's not important here. And then we get to the P, 6p, so we're back in 6 because P's are normal, and we're going to have 6p2 because we just go through these two. And then we stop. We're not going to do all of these because lead doesn't have that many electrons. So that is how you do electron configuration. And I hope that makes a little bit more sense now after all of the explanation.